Good evening, everyone. This is Sonu Singh from Skill Desire. Welcome you all in today's session. Skill Desire is real-time skills, innovation, plus opportunities. Guys, today's session is on electric vehicle battery pack design, and our expert is Mr. Pranav. Before starting the session, I would request everybody to please keep yourself muted throughout the session for a smooth conduction of the session. And at any point, if you have any doubt, you can just unmute and ask. Otherwise, put in chat section. We'll take that out during question answer session. So I request Mr. Parna to please start the session.
Yeah, okay. Hello, everybody. Am I audible?
Yes, you are audible.
Okay, so I'll just give a brief introduction about myself before starting the webinar. And then I'll mostly turn off the video because I don't want to be any network issues here. So
Okay, no issue.
basically, I'm working for Motors currently on battery pack design. And before this, I was working in Tata Motors on Nexon EV project and Tigor EV project. So I've been working on battery modeling, battery packaging, battery testing for over 2.5 years. And I'm also studying my master's. So this is my final year. And as a part of my final year, I'm also developing a innovative battery pack. So I cannot disclose the details for the same. But the project is sponsored by Dassault. So basically for the last 2.5 years, I have been very much involved in battery pack design, battery pack testing, new battery chemistries, and studying about EVs in general. And even in future, I'm planning to continue with a PhD course in similar field. Anyways, so moving ahead today, I'll be just giving a brief idea about how we on industrial level, how we consider a battery pack design for a EV. How do we decide how much should be the sizing of the battery pack? What should be the number of cells in series and parallel? A brief overview of that, and just a few examples related to that. Actually, there are some theoretical parts mentioned in the PPT, but don't worry, you don't have to read it all. I'll be just giving the pointers of whatever is mentioned. And then maybe later on, if Skill Desire allows it, maybe if the PPT is shared to you, you can refer to it as a part of notes. Okay. So, yeah. So I'll be not adding any masala or anything at the beginning, as you guys know that what are lithium ion batteries and how the present situation of batteries in case of EVs is. In case anybody wants to know a little bit more basic in general, maybe you can ask in Q&A during the Q&A session, or if maybe there could be another session which could be kept just on the basics of batteries, like what are the batteries and what type of chemistries are there. So as of now, we'll be just moving ahead with the design and the modeling part of the battery pack that we are going to focus. And as such, we consider 4 major inputs for this: the chemistry of the battery pack, the voltage of the battery pack, the average energy consumption of the vehicle that you're driving, and vehicle range, at whatever the desired range you want your vehicle to be. These are the 4 basic parameters that we have to consider whenever we are going to design a battery pack. Now, when we say voltage on here, the voltage is not actually just the voltage part, it is the entire energy capacity. So it's a product of voltage as well as the capacity in current, amperes. So we are going to, but both of them are relative. So we'll be seeing what is the difference in coming slides. So just a very brief overview that what are the basic components of a battery pack. As you might already know, there are electrodes, anode and cathode. There is a separator which is lying in between those, and the terminals, as well as the electrolyte which is filled in between. The flow of your lithium ion battery, like how the current flows, you might know that the lithium ions, they travel through the electrolyte, passing through the separator from anode to cathode and cathode to anode. And the electrons, on the other hand, travel from the outside circuit, which is basically giving us the electric current. And then on the other side, the electrons will again meet with the lithium ions, and the lithium metal will be as it is formed. So this process keeps on going to and fro, and your lithium ion batteries are charged and discharged. And these batteries are basically in 3 form factors. There is a cylindrical form factor, which generally comes in a hard case, steel case. You might have seen your domestic home, domestic cells in your remote controllers or in toy cars. So that is the size that this cylindrical cells for lithium. But those cells that we have at home, they are not lithium-ion batteries. I came across very a person from a very good company from OEM who asked me this question, that we use lithium-ion batteries in our remotes and toy cars. So I was laughing at that. So that's not the case. Those batteries are different. These batteries are generally not available in your day-to-day shops. Then again, we have prismatic form factor. In prismatic, there's a hard case and pouch. Now we can also separate this as just prismatic and just pouch, where prismatic is considered as a hard case and pouch is considered as a different category altogether. The difference is your pouch cell does not have any hard casing. It's just soft wrapped pouch cell, which is generally fitted in your mobile phone. You'll observe pouch cells in your mobile phones. And prismatic and cylindrical cells you'll mostly observe in your domestic applications and EVs. And they're also going to use pouch cells in EVs as well. The only issues with pouch cell is that pouch cell have a tendency to expand because there is no hard casing on the outside, so they don't have much mechanical strength. So this creates a very huge problem as a part of design engineers, because we are not considering the expansion into the design considerations. Then again, why only lithium-ion batteries? Why not the other batteries that are there? So you can see this is a Argonne chart, and it gives a basic idea about the specific energy and specific power. And the presently mostly we use lead acid batteries in our for small 12-volt supplies, or the other batteries at NIMH or nickel cadmium batteries in your remote control cars or domestic chargeable cells that are available. But the energy density of these cells is far less as compared to the energy density of lithium-ion batteries. This is one of the reasons why lithium-ion batteries are preferred. The very simple reason for this is also that lithium is the lightest metal that is possible. It is also the smallest ion. So the transfer is very easy, and at the same time, it is also lighter. So that is one of the reasons, along with some other reasons, which I'm not going to go deep dive into because this lecture is not about the chemistry of lithium-ion batteries. So directly we'll jump to the main part of our webinar. I was told that we don't have much time, so we'll be mostly finishing the webinar as quickly as possible, and then maybe we can spend some time on QA. So we'll jump to the actual design part, that how do we consider the design, that what is the amount of battery pack sizing that we should have. Previously, in the previous slide, we discussed the form factor of the cell, and we discussed the chemistry, that lithium-ion battery part. I just skipped one slide in between, that the chemistry of the lithium-ion batteries is further classified into different parts. There are LFP cells, there are NMC cells, and apart from that, there are LTO cells, NCA cells. A lot of cells are there. So I just removed that portion. There's a lot of difference in these particular cells in terms of safety, in terms of energy density, in terms of costing, in terms of life cycle. And we have to particularly decide that what is our goal for a particular application. If you're focused more on long range, or if you're more focused on safety of the vehicle, or if you're more focused on specific energy or specific power, based on that, these chemistries are basically selected. I had to omit that part as of now. So we'll just go for the actual calculation part that we are interested in as a from a designer's perspective. So even if you don't have any knowledge about lithium-ion batteries, still the main part, that how much amount of energy you require for a vehicle, this is the calculation for that. So now I have mentioned here that the current should be limited and the nominal power should be obtained by having a higher voltage. Now, since you students might know in your electrical subjects, what is the power in terms of electrical? It is V into I, right? So that is the voltage and the product of the voltage and the current. So even if your energy capacity of the battery is fixed, the voltage and current can be higher or lower. The objective is the product should be same. So how should we design the battery? Should we increase the current flow, or should we increase the voltage flow, which should be given the preference? So there is a catch here in both cases. If you increase the current amount of current flow too much, then that is basically, if you're trying to put more ampere in your battery, then you're going to have a lot of thermal issues, because your wires are going to get hot, your power losses are going to be huge, and also the size, the diameter of the wire is going to be more, because if you want to pass more current through the wire, you might have read the definition of resistance. In resistance, you know that resistance is inversely proportional to your area. Okay, so if you want to pass more current to that through that particular wire, then you'll have to increase the area at the same time. So that is not desirable for us at all. Then what do? We increase voltage. There is also a risk with increasing voltage, that is the safety factor. If you increase the voltage too much, there is a possibility that some person might accidentally, haphazardly touch the wire, or in case some accident may happen and the wires may get loose and it may pass some shock to somebody. And in such case, the safety is very critical. It could be fatal for a life. So when we are going for a high voltage design, there is a lot of safety norms and a lot of safety consideration that needs to be followed, but it is still preferred to have higher voltage over higher current for the obvious reasons that I mentioned earlier. Then now there is a particular drive cycle called as WLTC cycle. If you just run a small Google search, you'll find that there is this WLTC cycle, which is about 23 kilometers, and the entire path of 23 kilometers is divided into different sections: slow, medium, high running speeds. Plus, the roads are itself, the surface of the roads is also different. And this particular cycle, it basically gives a general idea of how the city life or a general drive cycle of any vehicle is particular on an average. So what we do is we take our vehicle, it could be of any class vehicle, like passenger vehicle or any other vehicle, and we drive it on this particular track. And we calculate the amount of energy that is going to be consumed on this particular track. Now notice there that for calculation of total amount of energy, it's not specific to EV. This drive cycle is specific to generally all vehicles. So if you can take any petrol, diesel, or any vehicle you can take, or whatever you want, and you can drive it on that track, and you can calculate the total amount of energy which is required to move the vehicle on that entire track. And whatever energy you're going to consume, that energy is basically going to be your propulsion energy. Okay, so let's just consider this is EP. That value we'll consider as EP. And for a particular 1.5 ton vehicle, passenger vehicle, the value is close enough to 140 watt hour per kilometer. It means basically you are consuming 140 watt hour per kilometer. And you also turn on auxiliaries in your vehicle, headlamps, radio is going on, AC is going on. All these auxiliaries are basically going to consume some amount of load. And so let's just call it as E auxiliary, which comes out close to 9.241 watt hour. The calculation is also mentioned above that your general cycle of half hour that is going on, it consumes some 430 watts, which is overall about energy of 215 watt hour over a period of 23 kilometers. So just divide this figure and you'll get this value, 9.241 watt hour per kilometers. So now you have the propulsion energy that is around 137, and you have the auxiliary energy that is around 9.24. So we know how much amount of total energy we are going to consume. And now we are going to design our battery pack based on this particular energy value. So let's just also consider an efficiency factor, that when you're going to transfer the vehicle from the energy from this battery pack to the motor to the wheels, there's going to be some loss. And for electric vehicles, this loss is not much. So let's just assume an efficiency of 90%, that is 0.9. So the formula for the average energy calculation is very simple. The propulsion energy plus the auxiliary energy multiplied by 2 minus whatever the efficiency we have considered. So this figure comes out to about 161 watt hour per kilometer. So basically, this is the amount of energy you are going to consume every kilometer, 161 watt hour per kilometer consumption. Before we jump to the next part, we'll just consider a few examples and few cases, how the battery pack design is there. So battery pack design, if you have seen that the cells are arranged in series and parallel, and if you most of the attendance and students, so you guys might be knowing this, that if the positive and negatives are connected continuously, then that is basically the series arrangement. And if the positive and negative, the same terminals are connected, that is basically your parallel arrangement. So you'll observe here that these battery packs, they're connected in such series and parallel combinations, and they fit into small modules. So just one simple example that can be seen here. A module of 4 cells is considered, and this module of 4 cells is further fitted into this large battery pack, which contains about 22 modules. So 22 into 4, that means 88 cells are present in this particular battery pack. Another example of Tesla's Model S battery pack. Tesla's Model S has 74 cells in a parallel group and 6 groups in series for a module, and every module has 16 modules are present in a series. Total number of cells are about 7,104 cells. If you multiply that 74, 6, and 16, you'll get this value. And the amount of voltage, you'll see that there are 6 groups and 16 modules. All of these are in series, That is basically 6 into 16 into 3.6. That is 345. That is close to 350 volts. So the voltage of your Tesla's battery pack is 350 volts. Okay. And the total amount of battery pack value of Tesla is about 100 kilowatt hour. Now, the cell selection in the 4 parameters I mentioned, there was a part of chemistry, okay, and part of form factor. So what we do is this is basically a chart of different cells. I'm not sure if it is visible for you since it's too small. Let's read it out. These are names of the manufacturers like Panasonic, A123, Molicel, Toshiba, Kokum, and the different form factors they use, that is cylindrical type of cells or pouch cells, and which kind of chemistry they're using in that particular cell. And what is the energy, what is the volume of the cells. Now, if you know the energy, if you know the volume, if you know the weight, you can calculate two things. First is the volumetric energy density, that is the energy, total energy per liter, and the gravimetric energy density, that is the total energy per kg. Both these terms are very important in terms of battery design, because we have a limited amount of volume we can fit under the vehicle. We have to consider that volume. And in terms of weight, our vehicle chassis has a particular capacity that it can handle so much amount of for this particular case, because as if you go on increasing that weight, there is going to be additional load on your vehicle, so it increases your overall design parameters. If you have to develop in terms of ride and handling, you have to go for a better suspension, you have to go for better braking power, because the overall momentum of the vehicle is going to be high if the weight is increased. So both the factors are very important, volumetric energy density and gravimetric energy density. We are presently also more focused on volumetric because we want to fit more amount of energy in less amount of volume. So some designers or some manufacturers focus more on the volumetric energy density, but they still have to consider the gravimetric energy density part. So coming back to the calculation that we were doing, so that we were here, we had calculated the energy consumption per kilometer as 161 watt hour per kilometer. So let's move on with that. Okay, let us assume that you want to develop an EV, you have to make an EV which travels 250 kilometers. I'm considering real life range, okay, not AI range. So let's consider that I want to go 250 kilometers, and I already know that what is my consumption per kilometer. Per consumption kilometer was 161, and I have to go travel a range of 250 kilometers. So what should be the total energy of my battery pack? It is very simple. Just multiply the two values. 161 watt hour per kilometer multiplied with 250 kilometers. That is basically 40436 watt hours. That is nothing but 40.44 kilowatt hour. So my battery pack size is of 40.44 kilowatt hour. This value is close to the battery pack of Kona EV, I believe, and MG ZS EV. Okay. So now we know what is the total energy of my battery pack. Next thing is I have to consider what is the total number of cells in series and what is the total number of cells in parallel. And as soon as we do that, our design part consideration is over. At least the basic design consideration is done. So how do we do that? I told you that we have already decided on a particular value of voltage, right? 400 volts. For a very basic example, let us assume that my cell has a voltage of 4 volts. One cell has a voltage of 4 volts, and I have to make a battery pack which is having a voltage of 400 volts. So if I arrange cells in series, my voltage goes on increasing. So if I want to reach a voltage of 400, just 400 divided by 4, that is basically 100 cells. So I have to connect 100 cells in series. This is a very simple calculation that we can do to obtain the number of cells in series. Now let us say we have the number of cells in series, that is the voltage is available to us. We have the total energy consumption in the battery pack, that is 40.44 kilowatt hour. So the next part is to calculate the total number of cells in parallel. I have probably missed to mention here, but I already told you in the beginning of the slide that the total energy consumption in kilowatt hour is nothing but voltage multiplied with ampere, Ah capacity. That is mentioned on your cells. You'll see if you buy a small cell in a domestic shop, it'll have something written like 2500 milliampere. So that milliampere is nothing but the current capacity basically. So we have to find that current capacity right now. We have the total amount of battery pack size, that is 40.44 kilowatt hour. This is the total energy. We have voltage. What is the total voltage available? If you just divide the total energy pack, we just divide with watt hour for ease of calculation with the total voltage of the vehicle that we have considered, and you will get the number of amp hours in the battery pack. Now, let us say we do that and we have the amp hours. I think I should have opened a calculator here, but never mind. So that's fine. So if you do that, you'll get the total number of overall total capacity of the cell in AH. AH is in amp hour capacity, current capacity. You know the current capacity. Now, I told you earlier that when you connect the cells in series, the voltage increases. So what happens when you connect the cells in parallel? So simple. If you connect the cells in parallel, you're going to increase your AH capacity. So if my cell, it is having an ampere capacity of 3 amperes, and if you want to make it 30 ampere, you're just going to connect 10 cells in parallel. Okay. But earlier, before this, what we have done, we have made a string of 100 cells. Remember, we have made a string of 100 cells, which is basically to obtain the required amount of voltage. And now this string we are going to keep adding in parallel. So 100 cell series we will add one more string of 100 cell series and we'll connect those two in parallel. Then again, we will add one more string of 100 cell series and we'll connect it in parallel. And we'll keep on adding these 100 cell series in parallel as much as times till we get the total amount of ampere capacity. So the same calculation I have just mentioned here, it's too much to read. So let's just not read this as of now. Just basically what we have to understand is, once we have the total amount of energy available, once we have the total voltage available, it is very easy to calculate AH capacity, total energy divided by 4 volts. And once you get the amount of AH capacity, you just have to divide it with single cell ampere hour capacity. That will give you the number of cells in parallel. And you have the number of cells in parallel, you have the number of cells in series, you multiply both, you'll get the total number of cells. So this concludes your cell arrangement, your total number of cells, your total number of cells in series, or total number of cells in parallel, as well as the configuration of your battery pack. Okay, now once we do this, we have to just focus on the last part that I mentioned earlier, that is the mass of the battery pack and volume of the battery pack. Now, when we have to consider the mass of the battery pack, what we do is very simple. We have the total number of cell, we have mass of one cell. This MBC is basically the mass of one battery cell, and MBP is the mass of the battery pack. So just multiply the total number of cells, multiply with the individual cell, you'll get the mass. But this is just the mass of the cells. What you have to add to this, you have to consider the thermal management mass, the fluid which is going to be there, the pack which is there around it, that part we should be considering. And one more thing we have to consider, volumetric. What is the total volume of the battery pack? In terms of volume, it is not that difficult. You know the volume of one cell, you multiply it with the total number of cells, so you're going to get the pack volume. But we have to consider one more additional thing here. When we are going to arrange the cells, they are not going to sticking completely together, which is there is going to be some gap in between there. Okay, and we have to consider this. So if, let's say, if I'm having a cylindrical cells, I'm not going to assume it as a cylinder, I'm going to assume it as a cube. What I'll do is, if I have a 18 mm cell, I will consider it as a cube of 20 by 20 by 65, and I will calculate the volume of that. So that will also consider the gaps which are present in the pack. This helps me plan for my thermal management spacing and other overall actual volume spacing. Okay. Normally, when we are doing this designing for cylindrical cells, we consider that. In case of prismatic cells, generally they don't consider it, because prismatic cells are most likely attached very closely to each other with some thermal management cold plates placed either in between or placed at the bottom. So if the cold plate is placed in between the cells, that's not going to take too much of volume, but they do consider that additional amount of thickness, but that is easy to add into the calculations. But for cylindrical cells, it becomes complicated because the shape is not a cube, so it does not fit very properly. So what we do is we just assume that cylinder to be a cuboid, and we calculate the volume in terms of cuboid only. That is always better for us. So yeah, thus concludes our overall packing. And these are the few references that you can refer that I have used for this particular webinar. As I mentioned, that I have not added too much details. I just try to keep the crisp part of the design itself, that how you are going to design the cell parameters, how you're going to just design the number of cells and the number of cells in series and parallel combination. Basically, that's all. If you're going to study more into this part, you'll have to focus on the chemistries and the life cycles of the battery pack. This goes deeper down into the chemistry study of the battery packs. But you can refer these resources and this website xengineer.org, which is this website. This particular presentation has been taking most of the content from this particular website, so that you can refer. It's very good. It has overall part of the EV development as well. So that's all. We can start the QA if possible. So
Okay, thank you for now. Actually, it was very nice session. So guys, if you have any question, you can ask. For now, we can stop screen sharing. You are muted.
it's fine. I'll just keep it as it is. If they ask any question, I have to move to that particular slide. I'll just go there.
Okay, no issue. Any question from your side, guys? For time being, for now, I have one question. Suppose I want to start my career in electrical vehicle industry. So, as a fresher, what path will you suggest me? How can I start my career?
So, really good question here. Now, what I told you is not going to help you directly in terms of career development, right? Because this particular part that for battery pack design is good, but we have to be have some additional skill sets. Now, it depends on what particular zone of the EV part you're going to be focused on. If it is battery, in battery itself, there are going to be numerous parts. It could be just the actual battery design from the chemistry point of view. So if you're a chemical engineer, basically you can focus on the different types of chemistries and the future lithium ion batteries and the solid state batteries that are getting developed. You can have a project based on that. If you're a mechatronics engineer, or if you're a mechanical engineer or electronics engineer, it's better for you if you guys consider a BMS side of it. Battery management system. Battery management system is basically nothing but it's a chip which is going to be the brain of your battery pack. So for BMS development, I think a lot of students and a lot of industrialists, they use MATLAB and Python coding. So MATLAB and Simulink, because I remember when I was in Tata, we used to have the entire BMS development done on MATLAB Simulink itself. So if students are skilled in MATLAB study, basically focused on the BMS development, it's really good. Then if you're into data science, if you're into machine learning part, that is again a good part, because what you can do is you can develop algorithms using Python coding languages. Even for computer engineers who want to get into EV field, what you can do is you can study machine learning, and we have seen some cases where we have to understand how much capacity degradation happens in a battery pack over the period of time. Your mobile phones are going to be losing the battery capacity over the period of time. You observe that. Same thing happens with your car. So your machine learning algorithm, it studies this particular pattern, that how much capacity fade is happening, and it gives you an updated range or updated data on your cluster, that my range has reduced to this and this particular value, or my capacity has been reduced to this particular value. So that is the part where machine learning or data analyst scientists can particularly focus on.
Oh,
If you are particularly just a core mechanical engineer part, then from modeling point of view, now this modeling point of view goes into a lot of things. There is a packaging part you can develop using CATIA or SolidWorks, where you can design the model, CAD model. Now, just designing the CAD model doesn't give us any credibility. We have to have additional part to it. That is the thermal management of this. So if you're able to learn some CFD software like ANSYS or Console or Star CCM Plus, you can try to learn CFD thermal simulations of battery packs. There will be some videos available on YouTube, or some data sheets or PDFs which are released by the particular software itself. And that will be really helpful, because industries are particularly focused on picking up graduates or picking up freshers who have those computer skills. Because you'll see that
excuse me, Pranav.
Yes, tell me.
You just stop screen sharing. If required, now we'll again share it, because the
Perfect.
discussion will look more engaging. Okay,
Perfect.
just stop that.
So do you have any other questions?
Yes, we have. Just stop the screen sharing once.
Okay, I'll stop it once again. Yeah.
Yes, it is fine. It is fine. So my other question that whether it is mechanical or electrical in core sector, students are much thinking that, or they are saying that core jobs are very less in market and salary is also less. So will you, as you are in core sector from past many years, so will you explain the present scenario?
Well, it's a really complicated section. See, the thing is, what the industries want and what the freshers are coming out learning from the college, it is not matching up. It is not syncing. Like you see, as of now, in case of EV market at least, there's no particular course in colleges that they teach particularly for EVs, right? The advantage students might get if they have a project developed already in EV that might help them, but otherwise there's a huge gap. So it's like industries want to pick people but they cannot pick people because there is no available skill set.
Okay, that means you are saying that jobs are there in market, but it is required to have a proper skill sets.
Yeah, skills are not there.
So it is very. I am very happy that at Skill Desire we are doing the same thing. Actually, we are bridging the gap between industry and
You got
students.
what you want. That's
Thank
nice.
you very much. Actually, you guys just motivates us. What is required in industry, that what we are teaching here. So it's glad. Thank you. And any other question from guys your side? Yes, Ravan, you can ask.
Yeah, you can unmute yourself and ask.
How to removing the range anxiety from EVs?
Okay, so this is a question which is on multiple levels. So just if you're talking about modeling part, if you are able to, even if you're able to give a range of 500 kilometers that is Tesla is giving, that still feels less, because let's say I'm basically from Pune. So if I want to travel to Goa, which is about 800 kilometers, I still have to stop in between. And if there is no charge or fast charging available, I'll have to wait for 10 hours for slow charging. So this is major reason that people have a second thought that they cannot buy EV as of now. So one way to tackle this is to make fast charging stations available on every particular, on all the highways at particular distances. Okay. Now, the just adding fast charging is not going to help us. We are also in the need of new development in terms of the energy density, in terms of capacities. So a lot of research is going on solid state batteries. That is, I mentioned earlier in lithium ion structure that we have a liquid electrolyte in between the cells. What we are doing is people are trying to remove that liquid electrolyte and substitute it with a solid electrolyte, which has a lot of advantages. One of them is going to help increase the energy density multifold. And if that happens, your vehicle might travel about 1,000 kilometers in a single charge. So that could be a boost. Plus these solid state batteries, they could be fast charged within 5 to 10 minutes because they have a thermal capacity of 200 degrees Celsius. You don't have to worry about thermal management as well. So in future, maybe let's say 5 years down the line, you will be having batteries which could be really good, which will travel thousands of kilometers and which will charge in 5 to 10 minutes. And then your anxiety might go away. But as of now, the only option present will be to increase the number of charging stations like Tesla did. If you observe how the marketing strategy of Tesla in the early years was, they put their own charging stations at their own expense. They were not waiting for governments to put charging stations. Tesla has their own supercharger line, and they planted it all over the American and Canadian parts. And this helped them to sell their vehicles because people were not worried that charging stations available. That is the only solution as of now, at least.
Okay, any more question, guys?
So, is there any battery swapping facility for the range anxiety?
Which facility?
Swapping facility, battery swapping facility.
Yeah, interesting. Actually, battery swapping is a very interesting concept here. If you are into two-wheeler, three-wheeler, or if you're into fleet management market, this particular battery swapping part has a very high demand, I would say, because it saves a lot of time. It saves the health of the battery. Now, what happens is when we try to fast charge your regular batteries, the fast charging results into degradation of your lithium ion cells. So your life of battery pack is going to be reduced over the period of time if you continuously keep on fast charging, unless it is properly monitored or if the technology is really good. So what happens in swapping stations, when you just swap the battery pack and the person who is removing that battery pack and keeping it in the station, swapping station, that swapping station has a thermal controlled chamber. In that, the battery pack is charged at a very uniform rate. And this results in a very good health of the battery pack. Plus, the swapping takes only 2 to 3 minutes. Just remove the battery pack, put it here, and but this can only happen for a small battery pack. You cannot place this. For example, for Nexon EV that I worked on, it had a battery pack of 250 kilos. So 250 kg battery pack, it is not easy to swap, and it is also not easy to put it in a station and then maintain it. So this can be possible for two-wheelers, three-wheelers, and right now I have heard a lot of news that some companies are tying up together to build swapping stations as a group project. So they will have same battery packs but different brands. This will be really helpful for people. And the vehicle will be sold without battery pack, and the battery pack will be given to you as a loan on a small amount of deposit. So this will help people financially as well, and this will also help companies.
Okay, any more question, guys? At last, I have one question. So last year was a totally talkative regarding pandemic COVID-19. So will you explain the electrical vehicle market after COVID? What is the impact of COVID or pandemic on electric vehicle market?
Well,
Or
COVID
with
has not
respect to
impacted.
job, I am asking.
With respect to job, now you put a very difficult complication here. In terms of market itself, COVID has not impacted EV market because EVs were not that good to begin with. But there was a rising growth anyways. If you have seen the sales of Nexon, they grew up to 3,000 in this even during the period of COVID. And at the same time, even other EV manufacturers like Tesla and for Volkswagen ID3 and not sure about BMW, but most of them, they showed a continuously growing graph in terms of these. But in terms of jobs, at least in India, I'm not sure because overall job market was hit in this COVID pandemic situation. So what people might be doing is they might be laying off people from one particular department and they might be using the internal resources for the job itself. So that is one of the reason why from job perspective, even though EV market is growing, job for last year were not that good. But for this year, again, there is a lot of pace because I've seen a lot of factories coming up in terms of battery manufacturing as well as in terms of EV manufacturing. You might have seen the news that Ola Electric is opening the largest factory in the world in Bangalore. So that's going to again create a large amount of job influx, and I have some contacts there, so the work there is going good. Apart from that, even in other places like in Gujarat, there's a factory going on, a tie between Leclanche and Exide is there. Amarja has recently opened an R&D factory for lithium-ion batteries. Okaya and some other country and some other companies in northern side also are developing, and I believe there are a few companies in Pune and Maharashtra as well who are largely focused and invested into this. In Delhi, there is Detail, I guess. Yeah. So all of these are showing huge potential, and if they keep on growing like this, there will be a lot of job influx for this particular EV sector. And as I mentioned, for this, if you're prepared with some amount of experience in this particular field, then it will be helpful.
Okay. Thank you. Any question? More question? Actually, we are running out of time. So for now, I think we have done up with the question and answer session.
Okay.
So on behalf of whole skill design team, I would like to extend a very hearty vote of thanks to you for excellent and informative session. Guys, before ending today's session, please make sure to fill the feedback form because your feedback and suggestions are most valuable to us. So before ending the session, I would like to add some point regarding a skill desire. As I saw or I observed from the session, Pranav rightly pointed out, the day has come where we have to talk about exactly real-time needs. So, Skill Desire is India's largest real-time learning platform where a student get trained by industrial experts along with placement slots and job-oriented trainings. So, I will request you all to focus on skills rather than job, because if you have proper skill sets, it will directly lead you to jobs. So guys, please visit our website for more detail, or you can directly contact on the number 8019692530 already share in chat section. And please fill the feedback form and waiting to see you all in our live session. Thank you very much. Thank you, Mr. Pranav.
Thank you, Sunny. So, if you have any questions, you can find me on LinkedIn or you can just contact me.
Yes. If you have any question, you can also directly contact on the given number. We'll forward you. Okay.
Perfect.
Okay. Thank you, everyone. Waiting to see you all in our live session where we are all set to explore electrical vehicle
Thank you.
job oriented course. Okay. Thank you all. Bye.